Hi folks, so let's talk a little bit more about getting solutions in the SIS model. So as we had talked about in terms of finding the steady state, we have an equation which relates the fraction of people that you're going to randomly meet who are infected to an expression which involves the degree distribution and parts of that degree distribution, as well as parameters indicating the relative frequency of infection compared to recovery. So what we need to do is see what this H looks like and then figure out what the steady state solution looks like. So again, as we pointed out, H is going to be a function where if we're finding, we want to find thetas that equal H of theta, then basically if we've got a situation where H prime at 0 is less than 1 and it's a concave function, there's going to be no steady state, and otherwise we'll find a positive steady state. So let's take a look at this function in a little more detail. So we want to take derivatives of this with respect to theta to figure out what its shape looks like. And if we take the first derivative of this with respect to theta, that's quite easy. And in fact, we'll find that this expression is greater than 0, and therefore we end up with an increasing function. So you can take the derivative here and verify that this is the expression you get, and indeed what we end up with is a positive function. And then if we take the second derivative of this function, then we get an expression which is less than 0. So here I'm not going to explicitly solve for the derivatives. You can go through and take those derivatives. It's relatively straightforward. These are just polynomial functions. Take the derivatives. The first derivative is positive. Second derivative is negative. And so here we've got a function which is going to be increasing and strictly concave. And that's going to tell us that the picture that I was showing you before is an accurate picture. And then the question is, where is this going to hit and have an intersection? So are we in a situation where if H prime at 0 is bigger than 1, then initially it's going above the 45 degree line. Again, given it's strictly concave, either we're going to have a steady state all the way up at 1, so we'll end up hitting up here, or it'll cross somewhere and have a non-zero steady state. Or if H prime 0 is less than 1, then basically there's no possibility of sustaining an infection. The only theta solution is going to be 0. And that's going to be in a situation basically where the degree distribution is putting weight on very low degrees and the lambda is fairly low, so you don't have much infection. That's going to be a situation where H prime has a fairly low derivative. So if we look at H prime at 0, we can plug in 0 for theta and then see what this thing looks like. And if we calculate H prime at 0, it looks out to be lambda E of d squared over E of d. So it's looking at the relative expectation of the square of the degree compared to the expectation of the degree and weighting that by lambda, where we recall lambda is looking at the relative infection rate compared to the recovery rate. So we have those expressions. And so the theorem, then we get that the conditions for a steady state process of the SIS model to have a non-zero steady state is going to be if and only if this lambda is large enough, and what it needs to be larger than is E of d compared to E of d squared. Okay? So you need the infection recovery rate to be high enough relative to the average degree divided by a second moment. Roughly think of variance there. So large enough lambda is going to give us a steady state that's non-zero. Now the interesting thing here is increasing the variance. If you do a mean preserving spread, so you increase the variance, that makes it easier to satisfy this equation. Right? So in the situation where we keep ED constant and increase E of d squared, then we're going to be in a situation where basically what we're doing is spreading out the degrees, but that makes higher degree nodes, which are going to have serve as hubs and be conduits for infection. And that aids in the spread of the infection and allows us to have a steady state that's non-zero. So if we think about this condition, then we can plug in what we know for various different models. And for a regular network, what does this turn out to be? Well, in a regular network, everybody has the same degree, so the expected degree is just whatever that degree is. The expected degree squared is just the expected degree squared. So in this case, for a regular network, E of D squared is just equal to E of D. Everybody has the same squared, so in that case, then you just need lambda to be bigger than 1 over the expectation. So in that case, the larger the expected degree, the easier it is to satisfy this. So that makes sense. And also, the larger lambda, obviously, the easier it is to sustain a positive steady state. For an Erdős-Rényi random network, if you work through what E of D is and E of D squared are for a Poisson random network, then you end up with a situation where the E of D squared is just equal to E of D times 1 plus E of D. So in that model, then we end up with, in this case, lambda greater than 1 over 1 plus the expected degree. If you work in a power law network, so if we have, say, for instance, we work with one where the density function looks like C times D to the minus gamma, then what we end up with is if you do a calculation to integrate that and look for the variance, E of D squared actually becomes infinite. And if that becomes infinite, then this whole expression becomes 0, and so we end up with lambda greater than 0. And so you basically always have a non-zero steady state. And what's happening here is in a power law network, at least in sort of the limit, if you have a very large network, you're going to have very, very large degree nodes. They're going to interact and always become infected and carry the infection through the society. So in that setting, you end up putting weight on the tails, and sufficient weight on the tails, that you always sustain an infection. Now, if you do a power law where you actually truncate the distribution and have some maximum degree, then you won't quite find this, but you'll find that that expression converges to 0 as you let that, whatever the maximum degree you allow in the society, to go to infinity. So in the limit, you always have a non-zero steady state in that model. And so basically what we find is the presence of hub kinds of nodes helps substantially in sustaining non-zero steady states. So the idea here is these high degree nodes are more prone to infection. They serve as conduits. Higher variance allows more such nodes, and that enables infection. And we see that directly in the theorem. So this is one of the kinds of insights that comes out of the SIS model, which is a useful insight and made explicit in this particular model. And it also then allows us to compare degree distributions, showing that if you have the same mean but you're increasing the E of D squared, then it's easier to satisfy these conditions. Okay, so that shows some insights that we get out of the SIS model. Next, we'll take a little more close look. So what this did is allow us to know when it is that we get a non-zero steady state. We can also ask questions about how large that steady state is and whether we can do comparative statics in that. And that's not going to be exactly the same kind of answer as just when there exists one, which was just looking at that derivative at 0. And more generally, we can go through and try and solve this model and say something about what's the average infection rate in the society.